Hello everyone, this is my day 2 of this challenge, and in this video I'm going to explain the time complexity and space complexity. At the end we will also see some of the patterns just to have the basic understanding of loops. So this is the time complexity and space complexity. Major portion will be covered in this video. What is time complexity? Firstly, the time complexity is not about the exact seconds which is taken in order to run an algorithm or a solution. Okay, so the time complexity is not about the exact seconds taken, but it is more about, and it is always about the mathematical measure of how the algorithm's running time is growing with the input size is growing. So if we are having any input value, let's say for n for a particular problem as given, so if as that input size grows, with that what is the running time algorithm, what is the algorithm's running time grows, that's the time complexity. So time complexity is a mathematical measure of how the algorithm's running time grows as the input size grows. Now to understand this more better, just have a real example. So here just imagine that you have to pack some of the gifts. Okay, so just consider that you have been given with some of the gifts and you have to pack those. Now what you have to do is you will just check these gifts one by one. So let's say you have taken one gift, then you have checked, then taken another gift, you checked, third gift you checked. This is how, let's say, n number of gifts, or just consider for now that n equal to 100 gifts are there, you will be checking those. It means 100 operations you will be required. Now let's say that gift increased by 1. Okay, number of gifts, so it becomes 101. Now you will require 101 operations, then you will require 103 operations, 102, 103, likewise 100 200, or then more. So if the number of items, number of gifts, if they are increasing, then you will also have to increase the number of operations, and as the number of operations increases, the time in order to finish those particular operations also increases. The same point is mentioned here. The time taken to finish the operations increases as the n grows, as the input size grows. So that's how we are seeing that the n value is increasing just linearly. Okay, so if it is increasing linearly, then we can say that the time complexity is big O of n. We will just see that what are the big O notations, theta, that all. So this is how we represent the time complexity as big O of n if it is increasing linearly. So that is the linear time complexity. Now this example is also mentioned here that if we are running a loop for n times, then the time increases linearly. That is big O of n. Now just consider a case where we are given with same number of gifts, but we have to now check every pair. Like we will, out of those n gifts, we will take one gift, we will compare it with all other n minus one gifts. Similarly, we do for second, for third, for fourth, and this is for n number of gifts. So if you are taking every gift, and if you are making every possible pairs, whatever they can be made, so that's how we are checking for every pair. And it means if for one we are going for n minus 1 comparisons, it means for n you will go for n minus 1 comparisons. Okay, so that, sorry, n into n minus 1 comparisons for n number of gifts in total. So that will be n into n minus 1, which will become n square minus n. And we will just see that what are the dominant values we take, what is the lower values, why we avoid. So that's what we will see here. Here we can see that the time complexity is big O of n square. Okay, the same example is also mentioned that if we are having a nested loop where two for loops, one loop inside another loop, that's running for n into n times. So that's how the time complexity goes to big O of n square. Now here is a simple example I have taken, that let's consider we are having some of the values and we have to sum all those values. And in that case, I will just use a sum variable, and in this run the for loop. Now I will take every value, will sum it inside the, just add inside the sum, another take another value, will sum inside the this values, this sum variable. Now we can see here that inside this loop, what it is happening, we are just running this particular, just executing this statement, initialization only once. Then after every value is just checking the condition, it is adding inside the sum and then incrementing. Again the value is condition is checked, then it is added inside the sum, and then it is again incremented. So we can see in this loop three operations are performed. Okay, so if the three operations are performed for one value, then every time it is operating for 3 times, and for n number of iterations it will be performed for 3n times. So you can see that the time complexity is going to big O of 3n. Okay, this is how as of now. Now just come to the some of the points which we should just remember while computing the time complexity. So whenever we are computing the time complexity, firstly we can see here that whatever the time complexity we are computing, they can be either for the worst case or average case or best case. So they are having their respective notations, like big O for worst case, theta for average case, and omega for best case. So here the time complexity, whatever we will be calculating, computing, whenever we write any algorithm or solution, we just go for the worst case scenario, because we have to make the safe guarantee that yes, the solution I have written, it can also be run in the worst case. It will not be failed. So the first point itself is that we have to check for the worst case scenario whenever we are computing the time complexity. Okay. And second is avoiding the constants and avoiding the then lower values. Just uh, here first point is mentioned here, and just stick to that as of now. So why we are going for the worst case scenario? Just I have mentioned as now as earlier, that whatever the solution we are writing, the input size, whatever the n value is, it can grow by the time. And if we have to also work for the greater value of n, or for the difficult n value, so in that case, if the input size is growing, then we have to write a solution that it should also work for that value. We cannot write for the average case itself that yes, this is the n value and we can write this. Now even if the particular n value is increasing, then that case will be failed, obviously. So the same point I have mentioned here, you can read also, that we mainly use the worst case time complexity just to give a guaranteed upper bound on the running time. Okay, whatever the n value can be at maximum, or for the difficult n values, and it ensures that the algorithm won't perform badly even for the most difficult inputs, and which is essential for the correctness, reliability, and security. And the average case, obviously it depends on the assumptions whatever we make, that this is the n value, we can write the solution for this, but it will not always hold, because n value can increase. Okay, so the worst case is always provides a safe guarantee. This we have understood for the first point. Now let's get to the second point: avoid the constants. So why we are avoiding the constants? So just imagine that if we are considering the constants, then it means we are saying that if we are considering the constants, it means we are saying that we are machine dependent, because the constants are something which depends on the machine to machine, or compiler to compiler, because they are having their separate instruction sets, they are having their different operations, micro operations they can perform. So it means if we run our same solution on the different machines, it will perform different number of operations. So it means we are saying that if the constants matter to us, it means we are uh, saying that our time complexity will depend on the number of sorry, it will depend on the machines. So we cannot do this, we will have to avoid the constants. Okay, so here it is also mentioned that big O notation, the which represents the worst case scenario, it ignores the constants and uses the worst case because it focuses on the long term growth. Okay, and whenever we avoid the constants, we can look our that notation what we are writing, we can look it in the a more broad manner, that how the how it is changing as the input size is growing. So that's the thing. And it also provides the machine independent, okay, and safe and reliable performance guarantees for any input and any system. Now also for the lower values, we can, the third point which is mentioned, that we should also avoid the lower values, because just in case this particular expression is written, and we can see that just we can take, if any n value, let's say 10 to the power 5. Now if I try to compute it, then it will become 3 into 10 to the power 5 square, that means 3 power 10 sorry, 10 to power 10. Now if we see as comparison to 10 to the power 10, the 4 is very small, it is not making any of the change in this, like very large change. So we will just uh, we can just neglect this particular value, the lower value. And also this 10, and it also becomes negligible in comparison to this 10 power 10, so we can also neglect it. And at the end, this 3 into 10 power 10, now we can see again the constant is here, so constant we should avoid, obviously. So it will just become big O of n square, because it dominates here. Okay, this is all about the 3 points which we should always keep in mind while computing the time complexity for our solution. Okay. Now here are some of the points you can also see here, that already mentioned about big O measures the growth, not the actual time. Okay, this is we have already seen. We have to ignore the constants and lower order values, lower order terms we have to ignore. We have also seen this. Okay, we will come to this when we are seeing for the important points. Now coming to the space complexity. So the space complexity is see, the space complexity can be like space can be of two forms. Whenever we are writing the algorithm for a particular problem or a solution for a problem, we are given with a problem where already the particular memory is given to us. Like the input space which is already given to us, that we do not count in the space complexity, because that is already given to us. And we, whatever the additional memory which we are using to solve the problem, that's how the additional memory our algorithm needs as the input. That input size, as it grows, that's the space complexity. Okay, now the simple thing is the total space which is there, that we only consider this all auxiliary space. That is the only extra space which is required by the algorithm, which we take as a programmer, and not the input space, because it is already given to us. So we use the auxiliary space complexity, that is the extra space. Now to understand it more, see, just consider the same example which we have taken here. Just consider the same example, that we are having some number of gifts. Okay, so we are given with the gifts already, we are having the input already, so we will not be considering that, we will not count that. Now whatever the boxes or whatever the material we require in order to gift them or pack them, sorry, to pack them, that will be the space, or we can say the material which is required in terms of this example. So that we will count. We will not be counting the input which is already given, that is the gifts, they are already given to us. But the boxes or any material which we are using, that will be counted as the extra material. So this is the example, you can just relate to this. Now see, just getting to the time complexity back, in any of the problem when we are writing the solution, what happens is, when we write them on the platforms like LeetCode and all, so on that their servers require 1 second, they takes 1 second for performing the 10 to the power 8 operations. It happens on these particular platforms. So what will be my mindset is that whatever the time complexity I am given with, sorry, whatever the problem I am given with, I will firstly write my algorithm, and I will just try to perform the operations. I will just try to check the operations which are required by my algorithm, and that's how it can be. Firstly, I will be checking the constraints which are given inside the problem, and then based on the constraints, let's say the n value is given as 10 to the power 5, which will go to maximum, and that's what the worst case scenario is. Now whatever the algorithm I have written, that will be like, let's say, if I have written a brute force for a particular problem, so it will be like big O of n square. Just take an example, if it is having the nested loops, so it will take big O of n square. Now I will take the constraint as it is given maximum 10 to the power 5 in worst case, and I will just put it inside my number of operations which I have calculated. That will be the number of operations which will be that 10, n square will be 10 to the power 10. Now I know that the 10 to the power 8 operations can only be performed in 1 second, but my algorithm which I have written, it is going beyond this value. It is performing 10 to the power 10 operations. Obviously the time limit is going to exceed for my solution which I have written. Okay, so I will not consider that as my better solution, because it is not performing to that extent, because the time limit is getting exceeded there. So this is a simple table I have made there, that whatever the complexities we are having for a particular solution we have written, and we will just consider it with, we will just have in the safe zone. So whatever the solutions or algorithms we have written, we will just try to find the total operations which it is taking, and will compare it with the 10 to the power 8. If it is coming more, it means the TLE is going to happen. Okay, so we will just use the input constraints whatever given in the problem, and we will just see our growth rate, how the time complexity is growing. Then we will just decide if the solution will run fast enough or not, or otherwise we will go to the next solution. So this is the table which I have already made there, that based on the time complexities. So if our n value is, we can just understand it from here. All here, see, the 1 second which I have already told that in 1 second the 10 to the power 8 operations can be performed. So using this particular check if our code will TLE or not. So here always check the input constraints. Yeah, if we are having the input constraints like this and less than equal to 10 to the power 5, then we can say that yes, uh, it will use big O of n, or it can use big O of log n. So which we can see here, that if it is going for big O of n, we already know that the 10 to the power 8 operations can be performed. So 10 to the power 5 is lesser than that, and also for n log n. Then coming to, if this particular constraint is given here, then we can say that yes, if it goes to n square, then it will go to maximum 10 power 8. it is okay, it will be performed. Now if n value is this less than or equal to 500, so if we perform n cube, it will just equal to like 1.25 or something, which will be into, which will come under this 10 to the power 8. That will be also enough. So that's how we see for the input constraints. And now there are some of the typical complexities to remember. Like for loop, it is having big O of n. If we write a simple for loop, for the nested loop, big O of n square. If we also write three loops in a nested form, so it becomes big O of n cube. Then for sorting, it takes big O of n log n. For binary search, it takes log n. For hashing average, it takes constant space only. Sorry, constant only for hashing. We are talking about time complexity. Now, worst case is used. Yes, this we have already seen. Now, yes, avoiding the exact operations we have already seen, which depends on the machine to machine. And we were checking for these particular values. So if this n is less than equal to like 10 to the power 7 or 10 to the power 8, we can safely use big O of n. Otherwise, if these values are given, like we can use n log n, which we have just seen here, these particular. And if it is 10 to the power 4, it can go for maximum complexity with big O of n. So this is how we can just see that our solution is better or not based on these values given as the input constraints. Okay, now just check for some of the steps just to have more better understanding on this. So just how to analyze for a specific problem. So firstly, we will check the input constraints, whatever the n value is given with. It means if this particular value is given for 2 into 10 to the power 5, it means it is safe for n because it is lesser than 10 to the power 8. N log n, it is also safe. N square, it is quite impossible because 2 into 10 power 5, it will go to 4 into 10 power 10, which is uh, absolutely impossible because it will just give the TLE. Then estimate the operations. Okay, so if we are using in your algorithm one loop, then it will take n. For nested loop, it will take n square. For sorting, it will take n log n, like this. So just compare with this 10 power 8. So firstly, you just check for the input constraints. Then you check for your algorithm that how many number of operations it's taking based on the input constraints. Then you will simply compare it with the 10 power 8 like operations or rule. If it is going beyond that, it means the solution or the algorithm you have written is not that better. It will occur with time limit exceeded. And yes, if it is equal or somewhat less, then you can say that it might work slow or it might work fast. So it depends on what the scenario is. So this is how you do, and these are some of the examples. You can just check here and what it happens. Now here are the simple examples just to have a quick recap of this. If the n value is given as the constant 10 to the power 6, then, and if you have to find the like maximum element, and in that case you can use big O of n which it can take big O of sorry, this 10 power 6 operations. Just example 2, if the n value is given here 2000, and if you have to find the pairs, then in that case obviously you will have to run the nested loop. So in that case it requires big O of n square. So it will take 4 into 10 power 6, which is quite safe here, lesser than 10 to the power 8. Now if you take n value as this 5 into 10 power 4, now here nested loops again occur. So again it will go to like big O of n square. So it will move to 2.9 into 10 power 9, and now it is going somewhat greater, so it will just be too slow. We cannot say that it cannot work, but it will be slow. Now it is just a borderline case as in this particular example. For matrix, let's say 500 cross 500, so if we use triple loop, then n cube, now it is again borderline but possible with the good optimization if we perform. These are some of the examples we have seen here, and I have also I'm also having this particular table also created graph where we can see the time complexities that how they varies with the size of the input data. So if our size of input data, let's just see for big O of n square, that if you are having one particular value, you are having let's say a value of n, and you are performing some operations. Let's say n value is equal to 10, and if you say that yes, if you consider big O of n, now if you will increase that particular value to double, if you double that value, let's say from 10 to 20, now if you see big O of n square, it will become 4 times. So that's how this n square is performing. If you take the value as n equal to 3 for like n equal to 3, then if you just make it triple to 9, it will just become 9 times. So this is how the n square is varying. So this is how every particular complexity you can check for. So as the input size is growing, as the input data is growing, the size of input data, just the time complexity varies for that case. How we have seen that. And here we have seen this particular points, that how the values, how to check for the time complexity. Like whenever you are solving the problem for a solution, you can check that the solution which you have written is correct or not. It will lead to TLE or it will perform well. So you can just follow these steps, simple steps. Just a small recap, that firstly you go with the input constraints. Just check for the input constraints, and after that, you whatever the algorithm you have written, just check for the number of operations your algorithm is taking. Based on that particular value, you just compare it with 10 power 8. If it is going beyond, it means the TLE will happen. Otherwise, maybe your solution will work well, might be slow or might be fast. That depends on what number of operations are performed. This is all we have just checked for this. Yes, recursion affects the time too, because the recursive calls are made. So the count, it counts the how many times the function is called. Obviously, if you are performing the recursion, like if you are finding the factorial of a particular number, in that case the recursion you will use. So the recursion calls which are made, that affects the time complexity also, and obviously it will affect the recursion is it will affect the space complexity. That's obvious. But we are saying for the time complexity, so it affects it, because how many times the function is called, that matters. And some of the extra points, some of the important points for this space complexity: no input size is taken into consideration, just the additional memory you have taken. The point, then what counts as a space? See, temporary variables are not counted as space. If we use any of the variables in our problem, in our solution, they are not counted. They are the temporary variables. Just the example which we are seeing, that if you are let's say just packing those particular gifts, just those gifts are kept on the table, and you are you just want to pack those gifts. Now if the gifts if the any of the material you are using, like you are keeping any book on the table, you are keeping anything on the table, that will not matter. Like it will not be counted as the space. Those we can just consider as the temporary variables. And you kept the book on the table, you kept the pen. But if you take any other box in order to just pack that particular gift, then that is used as the extra memory you have taken, extra space you have taken. So that's how the temporary variables, they are just treated as the constant space, with the constant space. And if we are using any extra arrays or vectors, then it will be counted as big O of n space we have taken for the n number of items. And similar with the maps and sets. So recursion stack, that is depth, whatever it is, that is the whatever the recursion calls, function calls we make, that space is taken in the stack. Then auxiliary space versus total space. We have already seen the total space is the auxiliary space, extra space plus the input space already given. But auxiliary space is the only space which is required as the extra memory which we are using. That is used, so we will solve the problem. And recursion uses the stack memory that we have already seen. Then the DFS recursion depth big O of n factorial, whenever we are finding recursion depth big O of n. Memory efficient patterns, like in two-pointer technique, when we will be doing here, the constant spaces needed. Okay, no any spaces required. And we are doing is in place sorting inside the original array itself. In that case, we do not use any extra space. That's how it works. And ignoring the constants and space complexity as well, we do not big O of 3, and we can simply write big O of n. And if it is written, we will just go of this n plus 100, we will just neglect the lower value. This is what we already seen in time complexity. Then this is the same table which I have just sent there. Same table is made here itself for the complexity. For what particular values, or what particular safe values for n the time complexity can be. These are the values, then we can use these particular complexity. The final 5-point summary is for the time complexity and the space complexity is that always whenever we are solving a problem, when we are writing an algorithm for a problem, we just have to check for the input constraints, what are they given, before choosing an approach to write that. just if you have seen a problem, you will just check that what are the input constraints. So yes, if we have just imagine that if we have found the n value as 10 to the power 5, let's say maximum value it can go, we can think of, yes, if it is 10 to the power 5, then I cannot use big O of a approach which is taking big O of n square time complexity. I cannot do that because it is 10 to the power 5 maximum. I will have to choose a particular solution which should have the number of operations either lesser than the 10 to the power 8 or even just closer to 10 to the power 8, because if I'm using n square, it will go to 10 to the power 10. This is not at all a good solution. It will lead to TLE. So this is how we see. And also 1 second, we already know that it takes big O of sorry, this 10 to the power 8 operations approx in the CPP. So yes, avoid we should also avoid the big O of n square when n is greater than 10 to the power 5. We can say that, see, if the n value is 10 to the power 5, we can maybe we can try to use big O of n square approach, where it might lead to the slower run. It depends like how the things are working, and we can just avoid the big O of n square approach. If it is just strictly greater than 10 to the power 5, we should avoid this approach for big O of n square complexity. Space complexity counts the extra memory like arrays, maps, stacks. It do not count the memory for the temporary variables. Recursion affects both the time and space complexity due to the call stack that we have already seen. So this is all about the time complexity and space complexity. Okay, so this is all about this. Thank you.